Okay. Let's see. As far as what's in my notes, I don't need to get terribly far. Of course, today, although my digressions always put that in jeopardy. But I do want to ask, I mentioned at the end of last class that you guys have seen enough material that the first homework problem can be started. Has anyone made an attempt at that yet? No? What?
The first homework.
Yes.
I've done the first homework.
Okay. Oh, like you got through it? Oh, okay. And you've not yet, or okay. So in other words, therefore, for none of you, there's a need to answer questions, right? Because yeah, if you've ever done it or haven't started yet, then correct? Okay. All right. All right. Because I was thinking, like, do I need to set aside time for that at the end? Apparently not today. So, well, and the first homework is mainly about other things like, finite difference, things I haven't covered yet. That'll start next week. And the first homework as a whole is not due for a long time, 3 weeks. So, okay, so I can just keep plowing through the notes and get this preliminary stuff over with. Now, okay, for sake of recording, okay, apparently I'm already spotlighted. So, so when I look at the video of this later, it better be right. The last time I was dealing with Laplace's equation and Poisson's equation. Okay, that was section 1.6 in the notes. Okay. Now, there are some very important properties of the solution to the Laplace equation or Poisson's equation that I should mention. And even though, like in this case, we're talking about these PDEs in an analytical sense, but when properties of solutions become known, it's a good idea, when possible, for any numerical methods to try to take those properties into account. So there's a certain property that the exact solution is supposed to have. If there's a way to design a numerical scheme to guarantee that the computed solution will have the same property, that's something that's highly desirable. It's not always easy to do because normally in numerical methods you're just striving for accuracy, of course. And if you have high accuracy, then chances are the solution will have whatever properties it's supposed to in the process by virtue of being accurate. But there's always going to be some error. And for certain problems, for those that come from modeling physical phenomena, it can still be very important to have for a computed solution, even though it has some error, to still remain faithful to the most important qualitative aspects of a solution. As an example, one of the equations, see it, a few minutes in, I'm doing my first digression. One of the PDEs I dealt with when I was at Stanford working with Marco Garrison, we're solving what's referred to as a pressure equation. The pressure is the unknown. And so a pressure in an oil reservoir. And the property that the pressure is supposed to have is that it is supposed to be never show any oscillation. It would be like, it should be like steadily decreasing, for instance. So if we tried to solve that equation using some higher order schemes, it may have introduced oscillations into a solution, which physically is not supposed to happen. Whereas a lower order method may not be as accurate, but at least was easier to guarantee that such a non-physical phenomenon would not happen. Because if you have solutions that behave in a non-physical manner, it really is kind of useless. So better to have a solution that might have a bit more error to it if it's faithful to the physics, for instance. Okay, so what properties do solutions of Laplace's equation have? So I guess let's start with properties of harmonic functions. I introduced the term harmonic functions last time. What do I mean by a harmonic function? That's a little one question ungraded pop quiz.
Constellation problem.
What?
Constellation problem.
No. Anyone else? Harmonic function.
The two boundary conditions are equal.
Or what?
On that way, the two boundary conditions are equal to each other.
No.
Differentiable?
Sorry, what?
Differentiable?
No.
Okay.
You mean the two boundary values being equal to each other? That's periodic boundary conditions. Okay. A solution to Laplace's equation is a harmonic function.
I was like sine, cosine.
Yeah. Now you said something about oscillations. Okay, but specifically it has to satisfy Laplace's equation. That's the key property. Okay. Right. Yeah, because sine and cosines, certain specific sine and cosines may satisfy Laplace's equation like on a bounded interval. Okay, so the solution of Laplace's equation. In other words, U is harmonic if and only if Laplacian of U is 0. All right. So there's two properties. First one is called the mean value property. Okay. So first I'll write out what the equation is. All right. Okay. So if U is harmonic, so that means that U of x is equal to either one of these two values. And there's a messy notation in here, but I'll explain it. Okay. Now, what do these two integrals mean? So, first of all, let's see what b of xr means. B of xr is equal to the set of all x, set of all y, such that the distance between x and y is less than or equal to r. So B is a ball in n dimensions, however many dimensions we're working in. So X is the center of a ball. R is the radius. So now I can explain what this integral means. So this is, when I take the absolute value, use the absolute value sign, over a region, it is the size of that region. So in this case, this refers to volume. So this whole integral, with this factor out front, is the average of u over the entire ball. Now, if you look at the first integral, it looks very much the same as the integral of u, but recall this symbol, when applied to a set, is a boundary. So this integral is the average of u over the boundary of the ball. So for instance, suppose we are in 2 dimensions. Here we're integrating a circle for first integral. Here we're integrating over the interior of a disk. But u of x is equal to the average of u over either entity, the interior of a ball or the boundary of a ball. They happen to have the same value when u is a harmonic function. Questions about what I've written here, what it means?
Yeah, so angle the average. You said the first integral is average over the boundary.
Yes.
And the second is average over what? I didn't get
Over the interior of the ball. So that's why I made to give a specific example of 2 dimensions. Just a circle or what's inside the circle. So these are averages over completely different entities, but they happen to have the same value. And u of x is equal to the value. So u of x is equal to the average value of u over a ball centered at this x. And regardless of radius. So if a radius is just, well, as long as the ball is contained within a region over which u is known to be harmonic. So if you're solving a Laplace equation on some funny shaped domain, and so if you use a solution, u is harmonic within that domain. But then if you choose a ball centered at a point in the domain, but the ball is large enough, like r is large enough, that it takes you outside the domain, well, u is not necessarily harmonic there. So in that case, this might not hold. But as long as the ball is contained in a region in which u is known to be harmonic, then this works. Okay. Actually, I think what I can do is give a simple example to illustrate this. So let's suppose that u of x is equal to mx plus b, just some linear function. Well, Laplacian in 1 dimension is just the second derivative. Second derivative of linear function is 0, so Laplacian of u is uxx, which would be 0 in this case. So this is our harmonic function. Now, so in one dimension, the ball with center x and radius r is instead of all y. Actually, I can use a different letter. Okay. I'll use let's use z, such that z minus x is less than or equal to r. So it's just the interval x minus r to x plus r. Okay. So now, so the average value on the ball, set at x radius r, which is just the interval, that would be equal to, you take the integral, x minus r to x plus r, of mx plus b dx, and then you have to divide by the size of ball. What's the size of this interval? Not 2x, but 2r. So I divide by that. Okay. So now I'll go ahead, so we just go ahead and evaluate this integral. So that's going to be 1/2 mx squared plus bx. You know what? No, I'm not going to do it that way. I don't have it right. Okay. The algebra is going to be too tedious. Mathematicians will go to all kinds of trouble to be lazy later. It's kind of our trademark. That is, whatever it takes to make this integral simpler. Also try to cut down on mistakes. So I'm going to make a change of variable. B is equal to let's see. Oh, wait. I need to use a different letter inside the integral. I have x in the limits. Okay. All right, so B is equal to z minus x. In other words, I'm moving x to the origin. So now the limits are simpler, minus r to r. And then I have m x plus v plus b d d. Anyone tell me why this is much easier to work with as far as evaluating the integral? What do I gain by doing that?
Symmetry.
Yes. Now symmetric interval. The integral over a symmetric interval of an odd function is 0. So I break this up. I have mv dv, and then the rest of it, which would be mx plus b, because keep in mind, x in this case is a constant, b is a variable. Okay. Polynomial odd degree. It's an odd function on a symmetric interval. 0. Here, this is a constant function. The integral of a constant function is a constant times the difference of limits. r minus of minus r, which is 2r, which cancels with this. So I get mx plus b. So the average is mx plus b, and u is mx plus b, so it's equal to its average over that interval. Questions about what happened there?
So what we're trying to show is that the average is equal to the function.
Yes. And please notice, it did not matter what r I picked. It's any r. Because u is harmonic on the entire real number line. So I didn't have to worry about that. So yeah, u is equal to its average over any interval centered at x is equal to the value of u at x. I can show the same thing in the boundary. That's easier in this case. So that's the average of, if I plug in the endpoints, have x minus r and x plus r. So now, if I average these two values, here I have minus r plus r. Those parts will cancel. So again, I will get mx plus b. So it doesn't matter whether I chose the interior of this interval, x minus r and x plus r, or its endpoints, the boundary of that interval, the average in both cases is equal to u of x.
So, okay, this is the average, the one on the side is the average on the boundary, right?
Yes.
And this is in the interiors.
Yeah, here's the interior.
Okay. So the interior is where we use the center and the radius.
Yes. Well, in this case, it just happened to be an interval.
Yeah, in this case, because it's a linear function, it's
Yeah.
the interior.
Yeah.
Okay.
On the example for the boundary, what does the first line say?
This
Yes,
average on boundary of b of x.
average on. Okay, I thought those were
Oh, sorry about that. Yeah, my
numbers.
is, those of you who've been subject mainly to my LaTeX notes are spoiled. Okay. All right. Any other questions? All right. Now, okay, I'll do a picture thing. Then I can talk about the other property. That harmonic functions have. Okay, so the second property that harmonic functions have is the maximum principle. Okay. It breaks down into two parts. So let's suppose we have a region omega, and we'll assume that it's bounded. So at least has a boundary. Okay. And we'll assume that U is harmonic. On omega. Okay. Now, what we have is the weak maximum principle. That because U is harmonic on omega, the maximum value okay. Occurs on the boundary. Okay. Now, we also have a strong maximum principle. And here we need an additional assumption. If omega is connected, and if there's any point in omega such that where the maximum also is attained, then U has to be a constant on the entire region. So in other words, if omega is connected, the maximum value can only be assumed somewhere in the boundary. Cannot be assumed in the interior unless you use a constant function in the whole region.
Once you connected, that means the closed boundary.
Connected just means that there's only one piece. Because you could define omega to be disconnected, where there's omega 1 and then a separate omega 2. Yeah. So a strong maximum principle does not apply to a region like that. Actually, I should be more precise here. When I'm taking a maximum, I should indicate omega with a bar over it. Can anyone tell me, when I take a region like omega and I put a bar over it, what does that refer to? See, it comes up in real analysis. No, not in this case anyway. Closure. Closure of a region includes the interior and the boundary. So here I'm looking at both when I'm taking a maximum. But whatever maximum that is, considering both interior and boundary, has to be assumed on the boundary. Now, if omega is disconnected, you can have a situation where in the different pieces, like if you find the maximum value in the interior of any of them, then on that piece, it's again constant. But in the other piece, it doesn't have to be. So that's why the strong maximum principle only has to assume that omega is connected. Okay. All right. Now, a very important application of a maximum principle. Oh, shoot. Okay. Well, first, any questions about this property before I talk about applications? Okay. So actually, I have applications of both properties to discuss. I forgot the one about the mean value one. Okay. How are we doing on time here?
These
Yeah.
are properties of both equations, not just Laplace.
Actually, everything I'm talking about now is only for Laplace.
Okay.
Yeah, it says we assume that U is harmonic.
Okay.
But all the applications will include Poissons. Okay. Oh, Actually, yeah, it's 3:05. Okay, we'll break here, and then I'll talk about the applications. I'm gonna fall behind again, aren't I? Oh, well, yeah, I think I'm going to. Maybe to ask you guys to remind me to not digress at certain junctures. Okay. Well, actually, that's a question about showing the example. I feel like that was a good idea. Okay. BRB.
So can I say anything else?
What?
Honestly, the change.
My notes?
Yeah.
Oh, yeah.
I mean, technically, since he's not in here, he doesn't have to enforce the master policy. If you just want to take it off and eat that.
I'll just shove it in. My hunger outweighed my math scores all. Would you like anything? I brought candy for my bingo winners. There's Reese's, Sour Patch, Twizzler.
I'm okay, thank you.
I had a Sour Patch and then tried a Jolly Rancher. And the Jolly Rancher tasted like it had no taste. But I think it's because I didn't get sour ones.
Yeah.
Because the Sour Patch was like so strong and then it was like, oh, this is not really good at all. Have you gone to that new like bento box place by Einstein's?
I have not.
It's like sushi, bento box, and something else.
I saw something about it, but I haven't been there.
I went there today and like it was good, but it's like $11 for like 2 dumplings, 4 pieces of California roll, some rice and meat. And it was just, I don't know, it was just small. For $11.
I mean, that's how I felt about there used to be a Mexican place right there, that's how I felt about that.
Oh dang,
Because
that'd be nice.
their food's like $12 or $13, but at the same time, you know, you could go to another Mexican place and spend the same amount of money and get more food.
Or get a foot long at Subway, for $5 or $6.
Yeah.
Yeah. That's annoying. Because it'd be nice to have normal food instead of sandwiches.
Right.
I should have tried my own lunch, but I didn't.
Yeah, I do if I actually remember to.
Yeah. Or if I haven't figured it out.
The problem is remembering to do
I have a quick question.
Yeah.
I was a bit confused about the change of variable you did.
Okay.
Because when we change the variable and change the limits, the same z and v disappear.
Wait. Okay. The original variable was z. What do you mean by disappeared? Like.
So the limit was x minus r to x plus r.
Yes.
And then when we change the variable from z to v,
Yeah.
that limit just simplifies to negative r to r.
Yes.
So, but there was supposed to be z minus x or z minus v.
Okay. So, I'm sorry. Since I erased it, can I please see your notes?
Okay, so I also didn't write that part.
Oh, any one of the notes?
Yeah.
Yeah.
Okay. I want to make sure that there wasn't anything. Okay. So, all right. So that's okay. Okay. I made a mistake, and unfortunately, I corrected it later, but it needs to be corrected here.
Mm-hmm.
It should be mz plus b dz, and then b should be, yeah, that's what's correct.
This is what I'm referring to. Over here, since v is z minus x becomes z minus v, right?
Okay. Yes.
So when z minus v goes here, we have z minus v plus r and z minus v minus r.
Okay. So, all right. Okay. Well, okay, so let's substitute z equals x plus r, and then I go ahead with that. Z equals x plus r, but now I replace z with okay, so then b is supposed to be all right.
Because when I did the change the variable, this limit becomes z minus v minus r, z minus v plus r.
Okay, yeah, that's definitely not supposed to happen. Okay.
Last
Let me go back to the board, please,
Okay.
and let's just straighten it out there, because people who are watching can't see.
Okay, yeah.
Okay, so, and that way to make dang sure that I did everything correctly. All right, so I have integral x minus r, x plus r of mz plus b dz. Okay. Now, here we have z between x minus r and x plus r. So now what I want to do is I need to subtract x from all sides. Okay. I call that b. So that's why I'm using that change of variable. So I let v equal z minus x. Okay, so then to get the new limits, I have z is equal to x minus r for the lower limit, for instance. But, oh, let me see what you have written down here. I think I see the problem. Okay, x is equal to z minus z. Okay, never mind. All right, so, but z is equal to v plus x. So v is equal to minus r, so that's why that's the lower limit. Yeah, so you set z equal to your original limits, then rewrite z in terms of your new variable v, and that's how you get the new limit. And it's similar for the upper limit. Right. But then z has to be rewritten as v plus x. Okay. Is that okay? Everyone else? Okay. All right. Okay. Now, what I was going to write here, applications of the two properties. Okay, first, for a mean value property, if I let's assume that u is in ck. Recall that ck is a set of all functions that are k times continuously differentiable. Then, when I consider the average over, let's say, the ball, that can be thought of as written as a convolution. It's a convolution of u with what is called a characteristic function. Now, a characteristic function is a function that is equal to 0 everywhere, except on some domain where it's equal to 1. So it's only equal to 1 or 0. The Greek letter chi is often used to denote a characteristic function. So a characteristic function in this case is equal to 1 if a function of y. Characteristic function of y is equal to 1 if y is in the ball. 0 otherwise. Okay. Now, the thing about a characteristic convolution The convolution has the effect of making a function smoother. So I won't get into the details here, but if u is k times continuously differentiable, the convolution of u with its characteristic function, the average of u on a ball, u of x centered on a ball at x, is in ck plus 1. So because averaging makes it smoother, you get an extra degree of differentiability or continuous differentiability. Now, in this case, because u is harmonic, I can't do this in general, but because u is harmonic, I can now say that u itself is in ck plus 1. What allows me to say this? I know the average is in ck plus 1. Why can I jump from there to say that u itself is in ck plus 1?
Because u is equal to its average.
Yeah, the mean value property. The average of u is in this, but this is u. That exclamation is meant to convey excitement, not factorial. So sometimes I get myself in trouble about that. But, so u is in ck. That means it's in ck plus 1. So because of this, what can I ultimately conclude about u and its differentiability and its continuous differentiability? So what's to stop me from going back up here with ck plus 1? And therefore using this logic it shows in ck plus 2. Yeah. So solutions of Laplace's equation, harmonic functions, are infinitely smooth. They have continuous derivatives of all orders. So that's what the mean value property gives us. Questions about that? All right. Next property, or application of properties, deals with the maximum principle. Okay. So, the maximum principle, first of all, that directly implies a minimum principle. The maximum must occur in a boundary. The minimum must occur in a boundary. And the way you can get that is you apply the maximum principle to minus u, because if u is harmonic, then certainly minus u is also harmonic. So now we can say that the maximum and minimum of a harmonic function must both occur in the boundary. Okay. Now, what we can get from that is the solution to Poisson's equation. Laplace of u is equal to f. Is unique. And here's how I can use the maximum principle to quickly prove it. Suppose we have two solutions. So my Laplacian is equal to u1 is equal to f, and my Laplacian of u2 is also equal to f. To prove uniqueness of a solution to whatever problem, you examine the difference. You assume there are two solutions, and you examine their difference. That's just a standard template for uniqueness proofs. So then I let V equal to the difference, U1 minus U2. So if I subtract both sides of these equations, I can say that minus Laplacian of V is 0. So the difference between them is a harmonic function, therefore is subject to the maximum minimum principle. But what if they solve Poisson's equation with the same Dirichlet boundary data? So I should mention, I'm talking about the Dirichlet problem. Okay. So we not only have these satisfied, but U1 is equal to F, and U2 is equal to F. Sorry, not F, G. Separate boundary data. All right, so Laplacians of both solutions or minus Laplacians are equal to F. U1 and U2 are both equal to the same function G on the boundary. But that would mean that V is equal to 0 on the boundary. But if V is equal to 0 on the boundary, and the maximum and minimum of V must be assumed on the boundary, there's no choice but for V to be 0 in the entire region. The maximum and minimum values must both be 0. So from there we can conclude that U1 is equal to U2, and we have uniqueness. Questions about this uniqueness proof?
Why are we assuming U1 and U2 equals G? So that's what we're trying to show.
Yeah. So we're assuming that U1 and U2 are both solutions of the same Dirichlet problem for Poisson's equation.
I want to show that U1 equals U2, right?
Well, you're given that they're equal on the boundary. You want to show they must be equal in the interior.
So why are you equal on the boundary?
Well, these are boundary conditions of a problem.
Oh, I see.
Yeah. So this is a problem that both U1 and U2 are a solution of. Poisson's equation with boundary conditions. Yeah. So the Laplacians are equal to the same right-hand side, same boundary data, then their difference is harmonic and 0 on the boundary. But because of a maximum minimum principle, the fact that it's 0 on the boundary means it must also be 0 in the interior. Right? There might be some lingering uncertainty, just want to make sure. Okay. Now, here's where Dirichlet boundary conditions, U is equal to something, some given function on the boundary. But I also need to talk about the case of Neumann boundary conditions, because that's a very different situation. Okay. So for Poisson's equation, with Neumann boundary conditions, so normal derivative is equal to h on the boundary. Then we have do not have uniqueness. And the reason why is if we do have a solution, U plus any constant is a solution. Because if I add a constant to U, I take a Laplacian, that'll be 0. I take the normal derivative of a constant, also 0. So once you have a solution, you really have a one parameter family of solutions. That solution plus an arbitrary constant. So it's like your plus C with integrals. Another issue is you actually might not even have existence. So there's a condition that is necessary for existence. Okay. So suppose I take the integral over omega, over the interior, of f, the right-hand side. Well, that would be equal to integral minus Laplacian of u. But the Laplacian is equal to, by definition, the divergence. The Laplacian is equal to the divergence of the gradient. Now, I try to give people writing time, but in case I don't, feel free to tell me to hold up a bit. So, anytime you have the integral of a divergence of a function, you can apply the Gauss divergence theorem, which states that the integral of a divergence in the interior is equal to the integral over the boundary of the normal derivative. But in this case, the normal derivative is prescribed by the boundary conditions. That's the integral of h on the boundary. So the integral of f over the interior must be equal to minus the integral of h over a boundary. This is called a compatibility condition. So you can't solve Poisson's equation with Neumann boundary conditions on the entire domain for just any old f and h that you choose. They must satisfy this compatibility condition. Then you can go ahead and solve it, and then even then that solution is not unique because you can add any constant to it. All right, so this right here is where I use the divergence theorem that is taught in multivariable calculus to get to that step. Question? That part of my plan for today was finish up what I had on Laplace's equation, which I just did, and then have both of class talk about the heat equation. And we have 10 minutes left. So this is unfortunate. Okay. So So I will start what I can.
So quick question before you.
I hope quick, please. Sorry, I just.
Yeah, I understand. We have ds. Is that arbitrary? Will there be any other variable over there?
It's customary to use s as the variable of integration when on a boundary, as opposed to using x for an interior. It's just I mean, what you really have would depend on how things are parameterized for a boundary interior surface or a boundary curve. But yeah, it's letters that people like to use. All right. Okay. Okay. What we have is U represents temperature, and D I'll refer to as our domain, and we'll assume that V is some arbitrary subset of D. Okay. Now, so this expression here, minus A times the gradient of U, I'll label capital F, is the flux across the boundary of V. So this represents heat energy entering or leaving the subset V. Okay. Now, we have an equation. Okay, it's actually this definition of flux comes from Fick's law. Fick's law states that the flux is proportional to the gradient. Now, what we have is a mass balance, so conservation law. So the mass balance states that the time rate of change of a total amount of heat energy within the subset V has to equal I feel like I might have a typo in my notes here. Oh, no, I don't. Okay. All right. Okay. Is proportional to, so this B here is just a proportionality constant. To the flux across the boundary of V. So capital F refers to the flux. This is the total flux for the region V. This is total flux on the boundary. Okay. Oh, I need to have a minus here to indicate direction. Okay. Now, because flux conveys heat energy that is in this case, entering V, we have to take the normal component because it's entering V along the normal direction that you have on the defined on the boundary of V. Now, as I just mentioned earlier from a previous example with Poissons equation, the integral over the boundary of a normal component by the Gauss divergence theorem is equal to the integral over the interior of a divergence sorry, I used the wrong letter here. That should be S, as is customary for a boundary, X for the interior. Okay. All right. So these are physical laws at work that that these two effects will balance each other out, because how does heat energy within a region such as V change? It comes from heat entering the region. And how can it enter a region? Prove a boundary. So that's why you take into account flux over the entire boundary. Okay. Now, I can substitute. So I have du dt. So here I'm moving the derivative with respect to time inside the integral. And I can do that because the region V is not changing over time. So now I substitute my formula for F. So I have divergence of minus a gradient of u. Okay. Now, a is a constant. I'll just pull it out. And then I have the divergence of the gradient. But as I mentioned a little while ago, that's the Laplacian. Well, now what I'll do is I'll put everything on one side. That equals 0. Now, this applies to my subset V. But the subset V is arbitrary. If you have an integral that is 0 over an arbitrary region, the only way that can happen is if the integrand itself must be 0. So out pops the heat equation. Where I define the constant C to be equal to A times B. So that's how the heat equation is derived. All right. I'll go just a little further and then stop for today, so that we're not as behind as I feared. Come on. I will stick around after to address any questions. I just want to get to this point so that I'm not under too much duress going into Thursday. All right. So just as Laplace's equation had a fundamental solution, I won't go to trouble deriving it in this case. The fundamental solution to the heat equation is 1 over 4 pi t to the n over 2 power, where n is how many spatial dimensions you have, e to the minus magnitude of x squared over 4t. Okay. And that is the solution to this problem. Phi t is equal to, okay, here I've simplified things to make a change of variable, or this constant c is equal to 1, just to declutter things a bit. And the initial data is equal to the Dirac delta function that we saw before. Okay, so this is the initial condition. Okay. So now I can use a fundamental solution to obtain a solution of the initial value problem in free space. So heat equation, Rn. So this is like a free space problem in one dimension. You can figure it as, call it a Cauchy problem. There's no boundary conditions. Okay, and then we have some given initial data. Okay. So the solution is a convolution of a fundamental solution with the initial data. So it's equal to phi convolution of u naught. Okay. And finally, phi and u are both C infinity functions, infinitely smooth. Okay. All right. So I'll cover the rest of heat equation on Thursday, and then get to the third kind of equation, the wave equation, transport. Okay, so I went over time. At least we're a little left behind. All right, so, okay. So I will see you Thursday. Well, I'll leave the recording going in case anyone has any questions. But